Hi and welcome to another Hopper internals video. If you're not familiar with Hopper, I suggest you back out to another playlist in my channel, like the Getting Started playlist or the Overview playlists. This video assumes you already know what Hopper is. I'm really soliciting input on my implementation of GPIO interrupt handling. I've recently been experimenting with this little device. It's visible on screen. It sits on top of a Raspberry Pi Pico. It's from Waveshare. It has some buttons, has a screen. So in order to support it, I bought it from the Pi Hut. It's made by Waveshare. In order to support it, I needed to add support for another driver, TFT LCD driver chip. And one of the reasons I was interested in it was to start to do something with buttons. So it could be for some application you're building, or retro gaming, whatever. So it's a cool little device, the way they've got it, and you can actually handle it quite well, just without even having a case. Anyway, I've already added the driver for the LCD. That's been committed, and then what I was working on today was how to implement interrupt service routines for buttons. So my first implementation of trying to mess around with buttons, I did like a snake game, sort of try and get the interaction to be reliable enough so that you sort of debounce the buttons, you don't miss any buttons. And then I realized pretty quickly that I need to do interrupt handling for buttons to make them work more reliably. So I went back to the Arduino APIs again and looked at how they're implemented in Arduino, and I came up with this attach pin API. So under our GPIO functionality, I added attach pin, and I'm using a Hopper delegate as the interrupt service routine. And looking at a lot of code online, you see that you get a lot of cut and paste and boilerplate. Like someone, they'll add 4 different service routines for 4 different buttons. And so I decided it's kind of handy to make the GPIO interrupt service routines capable of taking arguments. So my definition of the delegate for the interrupt service routine takes, you'll know which pin it was, and you'll know what the status of the pin was. In other words, these are this pin statuses according to Arduino. So it's, call when it's low, call when it's high, call when it's changed, call when it's falling or rising. So in the case, the most obvious, the usual case is just going to be you're going to set it up for a rising edge, and in the default implementation, it'll set the pins to be inputs, and it'll set their pull up correctly, so that you don't have to set them up in your setup and your initialize. I think I might still do that here though in my initialize. Anyway, it means I only need to have one ISR, one interrupt service routine for all 4 pins, and I just attach each of them by their GPIO pin number, and I made them all rising. And then in the interrupt service routine, I switch on the pin number and I just pick a color. So that implementation now makes sense that the first button is red, then green, then blue, then black. So what I was going to solicit in this is I'll show you the implementation now in Arduino, and that's where I'm concerned that I might, it's easy to mess this kind of code up. So let me show you how I implemented it, and you're most welcome to give me feedback and tell me I'm doing it wrong. most of the all of the code I put in one place here. It's in the top of the platform.cpp in our portable runtime for the Arduino platform. To get arguments to work, I needed to use a API that isn't very well documented in the Arduino community. It's because attach interrupt is well documented, but there's this thing called attach interrupt param, which takes the void pointer as an argument, and then when your interrupt gets called, you'll get that same parameter back. So it's a constant, but depending on which pin you attach to, you'll get a different param back, which means you can put useful things into that param. And in my case, I put in the address of the delegate, which is actually in Hopper, it's actually the index of a method. So it's not the address of the method, it's the index of the method, which will have to get resolved to an address before we can call it. But it's more flexible, and it's always 16 bits wide, whereas the address in Arduino is going to be 32 bits wide on the Raspberry Pi Pico. One of the problems is that this API might not exist on all Arduino platforms that we want to support. I suspect it will exist on the 32-bit platforms like ESP32, for example, or the S3 platform, the RISC-V platforms, and certainly exists on the RP2040 platform. That's what RP2040 platform. That's what I've been testing on. So I pass along as in my param. I pass the index of the method for the delegate. I pass along the pin number, which is kind of handy to know which pin was changed, and the status in case you're going to attach for different statuses. Button up, button down, for example. Right now I'm just doing button up. I'm catching button up. So I put those all into a 32-bit param. So 16 bits, 8 bits, 8 bits, and then in the interrupt service routine here, I pull them back out again. And you want this interrupt service routine to be as small and fast as possible, because during that interrupt service routine, your Arduino interrupts are disabled. And there's certain functionality that relies on interrupts, like delay functionality, milliseconds functionality, serial port I/O, anything to do with the USB port. So you really want to keep this as fast and brief as possible. Also, during an interrupt service routine, interrupts are disabled, I believe. So correct me if I'm wrong, but I've created a standard queue, STL queue here. STL is also not supported on all Arduinos. I mean, like the old AVRs don't support it, but I think it's supported on all the ones we care about. And I put these the parameters into a structure, and I push them into my queue. Could have just pushed a 32-bit int into the queue, but I reckon this is optimized, and it doesn't matter. So I don't think I need to protect access to the queue here, because I think interrupts are already disabled inside the interrupt service routine. So I can just append to the end of the queue another interrupt. So this is really quick. So you responds to the change on the pin and appends an interrupt to the queue, to this queue, which means I can go and service them somewhere else where I don't care about whether we've got interrupts disabled or not. Yeah, so this is the code for that. It's got a structure for the interrupt, the pin, the status, and what the delegate was, because we could be attaching multiple different delegates, and also a queue of the interrupts. I'm trying to also do this with considering other kinds of interrupts. Like, for example, I'll probably implement a timer interrupt so that you can say, call my delegate every 500 milliseconds, for example. So you could have a tick interrupt of some kind. So I wanted to make it sort of general. And then inside the runtime, on every instruction, we can probably find it quite quickly. Yes. So every time it's about to go and get the next instruction from where the program counter is, go and get the next opcode. Before it does that, it services interrupts. So again, I want this to be super, super fast because it's in the inner loop of the execution engine of the virtual machine. And it does it. There's two places. Warp is the, run outside the debugger, run super fast. And then this one, execute opcode, is called when we're in the debugger, which is why it's slower, but it can, it can check for breakpoints and things every instruction. So again, before it gets the next opcode, it services interrupts, which means that inside service interrupt, I can change the program counter to be somewhere else. And when it gets to this point, suddenly it'll be an interrupt service routine instead of the next instruction it was about to execute. And it sounded like, oh, that's pretty simple, that should work. And it did. So let's have a look at, so we've looked at how we service the interrupt, which is this interrupt service routine. We've looked at how we attach the interrupt to the pin. So we check that the pin is a valid pin to attach interrupts to, and it returns false if not. So you could check that value from Hopper. Switches it to an input and it pulls it up so that I think that this is the default in most of these things, is that they go low when you press the button. Most of these buttons are taking the pin to ground, and one of the good reasons to do that is it's the same for 5 volts or 3 volts, which is, you don't care what the pull-up value is, you care what the ground value. You pull them to ground. It's the safest way to do pins, pulling them to ground, not pulling them to VSS. And then here we have the service routine. So this is servicing the interrupts. So this is the bit that I'm wondering if I'm doing it right. Okay, so this infinite for loop is just really a block, so I can have a single exit point from this method. So every one of these breaks is exiting from the method. And I've just noticed a bug. No, it's not a bug. There it is, interrupts. So I'm checking. This is not safe in terms of being interrupted while I'm calling it. And I didn't make it volatile. When I tried to mark it as volatile, it also Arduino complained, but whatever, it's working right now. I do this check to check if we've got anything in the queue before I call no interrupts, because I don't know how fast, what an overhead we get from no interrupts. So if it changes to being not empty during this, who cares? It'll catch it on the next instruction. But if it does say it's not empty, then it'll fall through into here. And then I check again in case it changed, during my switching off interrupts. And now I know I've got control, so no one's going to interrupt me now. So if it's not empty and it gets past this, I can safely pull the front from the queue of the of my little structures in the queue. And I turn on interrupts here again because I only care about, this is only managing the queue. It's not really managing interrupts. It's managing the queue of future interrupts. So after that, I can continue at my leisure in the Hopper VM code. What this also means is that in Hopper, an interrupt can interrupt another interrupt. And I haven't seen a reason why not yet. So I don't see a reason why this would be a bad thing. Because these instructions are atomic. It only executes one full instruction at a time. So if in the middle of an ISR, if in the middle of the, to be clear, if we're in this, what it can do now is it can interrupt here. So during processing of the ISR, you might get interrupted and get called into another one, and then that'll return, and so you can recursively do these things. I don't see a downside yet, and it's, I didn't need to add 2 more APIs, one to say disable interrupts and re-enable interrupts. You might want to be able to do that to make something be, something that's performance intensive, not be interrupted. But I haven't found a reason for it yet, so I'm not implementing it yet. Let's go back to the Arduino. So yeah, how does it work? I get the index of the method. I save the program counter. I convert that method index into a method address, which is still actually 16-bit address because it's in the virtual machine. I push the arguments for the ISR, and yeah, what were those? So they were the pin and the status. the arguments of the ISR. And then I just set the program counter to the method address, which is effectively making the call. On entering it, it'll push the base pointer and create a stack frame. On exiting, it'll pop the base pointer, it'll restore the base pointer, and it'll use this as the return address. So there's no difference from returning from a regular method or returning from an interrupt service routine method. We could make a difference, like I said, if I disable interrupts, we'd have to make a difference between what the behavior of a interrupt service routine and a regular method, but right now there's no difference and I haven't seen a downside to it. So let's go back to Hopper. So if I build this F7, it's built it, and now if I launch the debugger, it's going to break what's running already, and it's successfully uploaded it. And then if I F5, we're now running in the debugger. Yeah, it's up and running. And if I go and press buttons, I'll change the colors. So, and yeah, as you can see from the program, redraw is actually doing this write line, which is writing to the serial port this message on each click, so that we have some feedback other than what's happening on the screen. If I Control C, my main loop is just, I've slowed it down slightly, so it's just not running off the rails here, but it's just looping in this continuous endless loop here. But what if I put a breakpoint over here? Let's put it, where should we put it? Let's put it on there. And then I'm going to hit F5, so we're running in that loop again. Now we're running in the debugger, as you can see at the bottom of the screen. And now let's hit the second button. And we hit a breakpoint. And what do we know? It says pin 17, which is correct. That's the second button. So pin 17 is the button which we're choosing RGB, the second button. Absolutely correct. And then if I press F5, there we go. We're running again, and it was the second button, which was green. So now if I press the third button, that's the blue button, we break, and in the debugger here on the right, it says that that was pin 2. Let's change the color to 15, which is blue, which is the least significant bits of my 12-bit colors, and that's absolutely correct. Yeah. So without much code and without much change, basically just setting the program counter to the start address of the ISR, pushing the two arguments, sort of injecting the call to the ISR into the inner loop of the virtual machine, and now we've got an interrupt handlers that work with regular Hopper delegates. So we're using a delegate as an interrupt service routine. There you have it. Anyway, let's switch back to this guy. I will put a link in the comments below about this device. I think it's a really good device to experiment with, in that it has TFT LCD. It's not a very high res one. It's 128 by 128, but I've played with text on it as well. It looks pretty good. And it gives you some buttons, and it only cost me, like $10 or something. And another thing, the Pi Hut ships really quickly to New Zealand. It's just very impressive to get stuff from the Pi Hut. Anyway, thank you for watching, and I look forward to feedback on what I've done wrong with my interrupt handling.